Hey everybody, we're here to discuss 4.2 page 4, in which we have a quintic function f of x equals ax to the fifth plus bx to the fourth plus cx cubed plus dx squared plus ex plus k. So we've got this long quintic function that has a standard form where a does not equal 0. And the reason we want that little a does not equal 0 is because that tells us that ax to the fifth is going to stay in the function. It's not going to go away. So the leading term has an exponent of 5, which, to answer the question, polynomial function of degree blank, we know that degree is going to be 5 because the leading term has an exponent of 5. And having that degree of 5, or being a quintic function, tells us a couple things about what the graph's going to look like. If we start with our 3 examples in the yellow pale boxes, as long as a is greater than 0, as we see here, as x approaches infinity, we get f of x also approaching infinity. So that's this up here going upwards. The same is true of the second example. And as x approaches negative infinity, f of x approaches negative infinity. And so there's our graphs going down. Now suppose instead we have a being less than 0. This is where you have a negative leading term. Our graph is then flipped across the x-axis. So as x approaches negative infinity, we instead approach positive infinity. And as x approaches positive infinity, we instead approach negative infinity. So just from the fact that we know a is positive or negative, we can determine where the function is going to end up on either end. This is called the end behavior of a function. Now let's look at the little green boxes. The first one says we have 5 x-intercepts and 4 turning points. Now the question is, what does that mean? Well, for x-intercepts, we see we've got these crossings. We can count 5 of them. So it crosses the x-axis 5 times. It has 5 roots or solutions, which is something we're going to go into later on. What we also have is 4 turning points. Now these are the places where your graph has sort of humps that switches from increasing to decreasing or vice versa. Those are going to be these peaks, these maxes and mins locally. And there's 4 of them for that graph. If you go to the next one, we have that there's only one x-intercept. It only intercepts once. And it also doesn't have any turning points. So even though we get a little flat area here, it doesn't actually change from increasing to decreasing. It's increasing, levels out, then increasing again. So we have no turning points for that case. And for the final one, we have 2 x-intercepts. Even though this first one on the left at -2 doesn't actually cross through, it's still intercepting the graph, even though it's flipping back. And on the right side, even though it flattens out, it is also crossing. Now we discuss turning points. This one is both a turning point and an x-intercept. Then we have another hump right here. And then the other x-intercept flattens out but doesn't actually change, so we don't have a turning point. We have 2. So from these functions, we have 1, 2, or 5 x-intercepts, given the graphs we have. And for turning points, we have 0, 2, or 4. Remember that this one right here wasn't a turning point. It was just a flat out. So I'll go ahead and delete that. And there's actually something to the reason why we only have even solutions for the turning points. That's something we'll go into a little bit later.